Tonight I'll be speaking about full text indexing and searching using Apache Lucene. So to begin with, let's go over the agenda for tonight. So to begin with, I'll do a brief introduction to Apache Lucene. Then I'll move on to speaking about inverted index, the basic foundation of full text searching. After that, I'll move on to briefly talking about scoring and ranking algorithm within Lucene. So then I'll go over the problem statement, the basic problem that I'm trying to solve, the big data problem that I'm trying to solve using Lucene for the purpose of this demo. Then I'll go over some code snippets, some code that I've implemented using the Lucene Java API. And finally, I'll move on to the IDE to go over the working demo of the code that I've implemented for both indexing and searching. So let's go over briefly on Apache Lucene, what the introduction of it. Lucene is a full text search engine. Unlike relational databases where the highly structured data can be searched using the ANSI SQL or any specific or database engine, SQL engine. Unlike that, full text search engine allows you to search for tokens within a string of words. In addition to that, full text searches allows you to search across massive amount of unstructured data in a very intelligent way. Which by that I mean, for example, you're able to search for phrases within a paragraph. You're able to search for words in proximity with other words. You're able to search for stemming and suffixes and prefixes of words, and so on. In addition to that, linguistic searches like conceptual searches or and also concept clustering can also be achieved using full text search engines. So Lucene is one of those many full text search engines out there, and it is fairly popular, and it supports powerful text queries including phrase searches, wildcard searches, range queries, proximity searching, and so on. It also allows fielded indexing and searching of unstructured data. By that I mean, if you're indexing a website, the website's field metadata, for example title or author or the meta tags, or just a Word document, like you are searching for a Word document, the metadata of the document, it could be like the date created, date modified, last accessed, and author, and the full text of it. So Lucene allows you to index them by field, and also it allows you to retrieve the data with full text queries by field or across the fields. It also allows you to combine structured and unstructured data. By that I mean, like if you have a file system full of massive amount of documents, and on the other hand you have database tables like Microsoft SQL Server, MySQL, or Oracle. Through connectors, you're able to combine that relational data with the file system data that you have. They offer faceting structure, like after you do a search and by fielded metadata, it can generate facets. And Lucene retrieval, like the searching part of it, it uses vector space model and Boolean ranking model for retrieval of the information. And it also allows pluggable ranking algorithm. For example, if vector space model doesn't return the most relevant documents that you're looking for, you can actually programmatically plug in some third-party probabilistic model and so on. It is also very memory efficient. You can configure it to store the entire index in memory, and retrieval would be very fast in that case. And also it's built on the Java stack. So if you're running an enterprise Java application, or with any framework. For example, if you're running Struts2 or Spring MVC, you can actually embed Lucene within your application, and you can configure it so it runs within the same JVM. So the performance is very efficient in that case. And in terms of licensing, Lucene is from Apache, and so Apache license is applicable in that case. So now let's go over briefly what inverted index is all about. Inverted indexes are very similar to the word count examples that we've done earlier in the semester. Given a blob of text, like given a chunk of text, like a paragraph, inverted index, in a very general sense, it calculates for each word how many occurrences, and in some cases it also calculates for each word how many occurrences and their positions within the chunk of text. So for this example that I'm showing on the screen here, it demonstrates that the list of words are gathered and as keys, and as values a list of indices of the words within the blob of text. And Lucene scoring, like any other search engine, the scoring is very important for Lucene, because in information retrieval, when you are searching for a document, the resulting documents and their ranking and their score, their weights, they should be relevant to the query that you are providing. That's how you get the most relevant information from a document corpus. Lucene uses a combination of vector space model and the Boolean model for scoring. So let's go over briefly the vector space model. So in vector space model, a document is represented by a vector of terms, and the terms may include words and phrases. And terms often do not include stop words or vowels. Stop words could be like the and the vowels and pronouns, and also terms are presumed not to be correlated to each other, and documents and queries in the vector space model are represented as two vectors. So in the next slide, so the terms may include words and phrases, and like I was saying, that two vectors, document vectors and query vectors. So they are represented as vectors, documents and queries. Then behind the scene, in the vector space model, Lucene does a normalization of the documents and queries. Then it finds similarities between the documents, and the in-depth discussion of this term frequency versus inverse document frequency, it's beyond the scope of today's demo, but this is a brief overview of what it does behind the scene. So now let's move on to the problem statement of the demo. So the use case that I picked for this demo purpose is reviewing a massive amount of Financial Times Magazine articles, historical articles, and I have the documents in XML format in the file system. So in order to review the document, there is a need for searchable index of the document corpus. So for my goal was to implement a Java indexer class to traverse through the folder structure and build feed into the Lucene index. And in addition to the indexer class, I also wanted to implement a search client on top of the Lucene search APIs to retrieve the index financial data set. So here is a sample document out of the document Financial Times article data set. So the documents are in ASCII format and also the, ASCII text files, and also they are in XML format. So in a way, the document that are going to get fed into the indexer, they're kind of structured in XML format. So in the next slide, I'll On this slide, you're seeing the folder structure. So I only have two folders, two buckets of articles from Financial Times. I didn't include the entire data set because the indexing could take some time, and that may exceed our allocated time for the demo. So in the next slide, the indexer class, this is a snippet of the indexer class. So I'm invoking the standard analyzer that Lucene provides out of the API. Then I'm reading the files and and creating the Lucene index. So soon we'll go over the code in the IDE, but this is a brief overview of what I'm trying to do. So searching across the index field. So this is a snippet of code that uses search. So you're probably noticing some deprecated method because I'm using a newer version, like the latest version of Lucene, which came out last week. So it's not really compatible when I started writing the code the week before. So now, so what happens in the indexer is that initially the indexer goes into the file system and traverses through using Sax parser. It goes through each file and extracts the metadata for each file, and it creates Lucene documents, and using a Lucene index writer, which is a class from the API, it writes to the index. So now let's go over to the demo. Okay, so here you're seeing, like I have like three packages, like indexer, searcher, and logger. In logger, I'm just logging for debugging purpose. So in here, the data loader is the driving entry point for the indexing process. So here you're seeing in the data loader, the main driver function, it has an input path of the the Financial Times article folder, and it has an output index, the destination index, and from here I'm calling the process file function. So that process file basically passes the directory list, like the array of files, to a different function where I actually use the Sax parser to parse the XML. So here, as you're seeing, the list of documents within each document, like in each document has a list of nodes, and these are the fields: document number and profile, date, headline, and the text of the document. So for each document, I'm going parsing those information, and with the information, I'm creating my own document DTO object. So document DTO object it's like a data transfer object that represents the document in a Java class, each XML document in a Java class. So then I'm passing the document object to a add Lucene document function that I have. Again, some of the functions are deprecated because of incompatibility with the API that I'm using, but they are backward compatible. So for each Lucene document, so Lucene document object, I'm using a document like Lucene.document.document object, and I'm adding each of the XML documents from the file system to this Lucene document, and for each document I'm adding into the index writer. So now if I run the data loader, so let me just run this. It will take just a minute. So as you're seeing in the console, it's indexing the documents. So in the two folders that I have in the file system, they contain about 10,000 of those XML documents. So for the 10,000 documents, I'm not using the memory data store. So if I use memory data stores, that would have been done within seconds. But for the file system and my hard drive not being a SSD drive, it takes about a minute to index the 10,000 documents. So inside the Lucene search, if I go to the input data folder, Financial Times, so each of these folders have these document, and each document contains multiple XML documents. So let me just open one of them to just to show how they look like, the input data. So this is how they look like. So here's the document starting tag, and here is the document end tag. So this is one document, and out of these metadata fields like a page, publication, text, headline, so each of these fields are being extracted and being indexed in Lucene. So I think we're almost there. And also then after that, the index data is being stored in file system. So which is, I define this as this index folder. So these are the index files. So there is an option also in Lucene API that it allows you to store the index entirely in memory. So retrieval in that case and also indexing in that case becomes very fast. So and also let me just go over, while it's indexing, let me go over the searching part of it. So after indexing is done, then we'll be able to use this class to run the Lucene search. So here again, the main driver function has, it's actually getting keyboard input from the end user, and so it allows you to search across the code that I've written for the search client. It allows you to search across all fields. Like if the end user is saying that I want to search for the word foo across all of the fields, then in that case I'm searching across all fields in the Lucene index. And so here is the code snippet where if the user included user request is searching across all fields, then I'll go over this snippet of the code where I'm actually first of all, I'm the multi-field query parser. It's one of the classes out of Lucene API where I'm actually parsing the query. In the then there's a query object. Then in the parser, the multi-field query parser, I'm using the Boolean operator for if there's a space in between my two search terms. By default, I'd be putting or in there, and also I could have done and as well. Then I'm getting the executing the search, like the mSearcher object here, which is the index searcher class out of the Lucene API. So I'm submitting the query and getting the results back, and with the results I'm looping through the results. So I have another block of code where I allow the end user to search, specify the field they want to search in. For example, they will if they want to search only in the text field, they will be able to do that. If they want to search only in the headline field, they should be able to do that. So now the indexing is done. So as you can see, it indexed about 10,000 of those XML documents. So now I'll real quick I'll demonstrate the searching client. So as I run the search client, it will prompt me with enter your search term. So I'm gonna enter something like stocks and Microsoft perhaps, and it will ask me, would you like to search in all fields? So I'll specify yes, I would like to search in all fields. Then it's initiating a search. Now it's got the results back in split seconds, and it's now returning, painting the hits, the document IDs. From there, within your application, you should be able to take this result set and paint the UI and represent the document to the end user the way you want to. So as you can see, it returned like 508 hits for this search term. So that pretty much concludes my demo, and thank you all for listening, and have a great evening.